Have you ever asked an AI a question and gotten an answer that sounds perfect, but just feels off? Like it's fluent but not quite right. That's the tricky part about large language models, or LLMs. They're amazing at generating text, but they don't always know if what they're saying is accurate. Today, we're diving into a groundbreaking approach that's changing how we trust these AI systems. So what's the problem? LLMs are like super smart but slightly unreliable assistants. They can write essays, code, or even poetry, but they don't have built-in truth checks. Imagine a chef who can make a beautiful cake, but sometimes uses salt instead of sugar. You do want a system to catch that error before serving it right. That's where this new research comes in. The solution: a contract layer inspired by design by contract, a concept from software engineering. Think of it like a recipe with strict rules. Before the AI starts generating, it has to agree to certain conditions. These contracts define what the input should look like, what the output must do, and even how the AI should fix itself if it goes wrong. Here's how it works. When you ask the AI a question, the contract layer acts like a quality control manager. It checks if the input fits the required format, like making sure you're using the right ingredients. Then, as the AI generates a response, the system verifies it against the contract. If something's off, say the answer doesn't match the rules, the AI gets a nudge. It might retry, adjust its approach, or even ask for more details. This process is probabilistic, meaning it's not 100% guaranteed, but it's way more reliable than before. What makes this so powerful? The researchers didn't just create a checklist. They tied these contracts to type theory, a branch of math that ensures data structures are logically consistent. Think of it like a grammar checker, but for meaning. If the AI's output is well-typed, it's not just syntactically correct. It's aligned with the semantic rules of the task. And here's the cool part. If two AI systems follow the same contracts, they're considered functionally equivalent. It's like having two chefs who both follow the same recipe. They might cook slightly differently, but the final dish should be trustworthy. This opens the door to comparing AI systems fairly, focusing on things like speed, cost, or how well they handle complex tasks. But it's not without challenges. LLMs are still probabilistic machines, so even with contracts, there's room for error. The research also highlights the need for better formal verification, like mathematically proving that an AI's output will always meet its contract. It's a work in progress, but the implications are huge. So why does this matter? As AI becomes more integrated into our lives, from healthcare to finance, we need systems that don't just sound right, but are right. This contract layer is a step toward making AI more transparent, reliable, and trustworthy. It's not about replacing human judgment, but giving us better tools to work with these powerful yet imperfect systems. Now let's zoom out. How do we ensure any complex system, AI or otherwise, does what it's supposed to? This question has haunted computer scientists for decades. Back in the 1960s, Hoare introduced Hoare logic, a framework to prove programs work correctly. Think of it like a checklist for code. Every step must follow strict logical rules, just like solving a math problem. But here's the twist. Traditional logic works for deterministic programs, where every action has a single, predictable outcome. What happens when programs involve randomness, like a self-driving car deciding whether to brake or swerve? That's where probabilistic program verification comes in. A 2002 paper by Den Hartog and de Vink laid groundwork for applying Hoare-like logic to probabilistic systems. They asked, how do we prove a program behaves correctly when outcomes are uncertain? Imagine a weather app that predicts rain with 70% accuracy. How do we ensure its logic doesn't lead to disastrous decisions? Their work showed it's possible, but it requires new mathematical tools to balance certainty and chance. Fast forward to today, and the challenge has only grown. Large language models like GPT or Claude can generate human-like text, but they don't understand logic in the way we do. A 2024 study asked, can we make these models not just guess but reason? Researchers developed self-aligning systems that explain their answers, forcing AI to justify its reasoning instead of just mimicking patterns. It's like teaching a student to not only solve a problem, but also walk through their steps, so we can spot if they're just guessing. But how do we bridge the gap between abstract logic and real-world AI? Enter neuro-symbolic approaches, a blend of machine learning and formal logic. One 2024 framework, Symbolic, combines generative models, which create content with logical solvers, which follow strict rules. It's like having a creative artist who also double-checks their work with a calculator. This hybrid method is especially useful for tasks like medical diagnostics or autonomous vehicles, where errors can be deadly. Meanwhile, researchers are rethinking how we test software altogether. Traditional methods often rely on rigid contracts that code must follow, like a recipe's ingredients. But what if those contracts could adapt? A 2020 paper explored dynamic contract checking, allowing programs to adjust their rules in real time, like a chef improvising a recipe while still hitting the key flavors. The big takeaway: verifying programs isn't just about fixing bugs, it's about building trust. Whether it's ensuring an AI doesn't spread misinformation or a flight control system doesn't fail midair, these techniques are the invisible scaffolding keeping our digital world stable. And as AI grows more complex, the need for rigorous verification has never been greater. Next time you interact with an AI, remember, Behind the scenes, there's a whole world of contracts, checks, and probabilistic nudges making sure it's not just talking the talk, but walking the walk.